Hi everyone, today we'll be going over day 11 of Advent of Code, including walking through the problem and showcasing my description in Python. Yeah, let's get into it. So for day 11, we're dealing with inputs that look like this, where we can sort of think of this as a 2D plane, where the dots represent empty space and the pound symbols represent galaxies. Um, and so essentially, our goal is to find the um, distance between each pair of galaxies, where that distance is calculated using like the L1 distance, meaning not like the shortest path here, but following like on grid lines. So for example, between this galaxy and this galaxy, the distance would be 1, 2, 3, 4, 5. Now, the added wrinkle that we have is that there's been some expanding in the universe, and each column or row that does not contain any galaxies is actually has like needs to be twice as big. So for example, we see in this third column there are no galaxies, so that's going to be expanded into two columns in um, this so our input looks like this, and then the true state representation looks like this. Um, yeah, so the we get a little bit more about the example. Um, but I think we can just get right into the code and how we want to solve this. All right, so what I'm doing here is in part one, I'm receiving lines to this as the function argument, where lines is just a list of um, the new lines separated strings. What I'm going to do first is create this list of the original positions of each galaxy. So this will be populated with, so we're looking at the original input. We can actually do that here, where this will have an entry in this list for each one of the galaxies. So this will be on row 0, column 3, and so on. This will be row 1, column whatever, row 2, column 0, etc. Then I create these sets where rows is the set of each um, of like the unique rows in the galaxies, and calls is the set of unique columns in the galaxies. So for example, rows will include 0, 1, 2, but not 3 because there are no galaxies on row 3. And so we'll use that then when we create this new list. Now this will be like what we can think of as the real positions of the galaxies, so the position of the galaxies on this list. And the way we calculate that is by taking the original positions and then offsetting the rows and columns by the amount of empty space. So for example, in this, we'll go for, yeah, this example first. If we look at the rows, there are no rows above it. Or yeah, let's look at this example instead. So if we're looking at this position, there are 4 rows above it. 1 row is empty, so its row index needs to be increased by 1 because this is actually going to be 2 rows. Then for columns, there are 1, 2, 3, 4, 5, 6 columns in front of it. Column 0 has an entry, column 1 has an entry, column 2 does not, and it looks like there are 2 empty columns in front of this. So its column index needs to be offset by 2. The way I do that is by just using this list comprehension, summing over all of the values not that are less than the row index um, in the sets in the row set, and then I just sum that. So this will just essentially be the row and column offset as I just went over. Then I append to the galaxies list. Finally, now we have the true positions of the galaxies. We can just get every pair. This is using itertools library, the combinations function, which will get us each pair of these, not and it'll only return one like pair. So it'll be, for example, it won't return like this galaxy. Um, like if we have, looking at this, like we only care about Galaxy 1 and Galaxy 2, we don't need to like think about that pair in the opposite order, like Galaxy 2 and Galaxy 1. I mean, yeah, if that's not clear, look at the documentation for iter_tools.combinations. Then to calculate the L1 distance, we're just taking the absolute value of the difference in the row coordinate and the column coordinate. We can return the total. So running that on our input, see that we get 102 ends with 66, and yep, that's correct. Now for part 2, we have this, or the problem stays essentially the same. The difference is that when we here we replace each row with 2 new rows. In part 2, we're replacing each empty row or column with 1 million. And so this would be challenging if you were doing something like, say, padding the input. Like another potential solution could be to take your input at all the columns that are, or all the rows that are empty. I could insert another row after it, and that wouldn't work now that we're making these a million times larger. But for our solution, it ends up being an incredibly simple change. All this code is exactly the same, except for when we're calculating the offsets, we're summing essentially. So when we increase the size and when we double the size, we need to add 1 row for each that's empty. And when we're increasing the size by 1 million, we need to add for 1 million minus 1, which is whatever, 999,999. And so that will give us our solution to part 2, 59, and that's correct. So yeah, I think this problem was pretty straightforward, and my approach to part 1 ended up working really well for part 2. That's it for this video. Please let me know if you have any questions or comments, and I'll try and get to all of the comments in the comment section. Alright, keep following for daily updates on Advent of Code, and I'll see you in the next video. Bye.